Welcome you all to the course Database Management System. Myself Mohammad Asifuddin Mondol, Assistant Professor, Department of Computer Science and Engineering, Narula Institute of Technology. And this is lecture number 33 of this course. In this lecture, I am going to cover chapter 7, which is Transaction Management System. And these are the topics which I am going to cover during this lecture. I'll discuss about the concept of view equivalent, then view serializability. Then I will discuss different types of schedules like recoverable schedule, cascadeless schedule, and then I will discuss a graph which is known as precedence graph so that we can test for serializability. Now, in my just previous lecture, I have already discussed about the concept of serializability. Also, I have discussed about the conflict serializability. But now in this lecture, I will cover about the view serializability. Now the conflict serializability as well as view serializability, what are their utility? If a schedule S is conflict serializability, or if a schedule S is view serializability, then that means the concurrent execution of multiple transactions based on that particular schedule S will make the database system in consistent state. That means even if multiple transactions are executed on the basis of schedule S, which is either conflict serializable or which is either view serializable, this concurrent execution of the transaction based on schedule S will lead the database system to a consistent state. So in this video, just I am going to discuss about the concept of view serializability, means what schedule is termed as view serializable. But before that, we have to know what is view equivalent. So first of all, we have to know what is view equivalent. Suppose we have two transactions, S and S prime. Suppose we have two schedule S and S prime, and both the schedule have same set of transactions. Now S and S prime, these two schedules are termed as a view equivalent if following three conditions are satisfied. So what is the first condition? It states that for each data item Q, if a transaction Ti reads the initial value of Q in schedule S, then transaction Ti must in schedule S prime also read the initial value of Q. This property is actually the initial read property. Now what does it mean? Suppose we have two schedule S and S prime. Suppose in schedule S, suppose a transaction Ti reads the initial value of Q. That means in schedule S, a data item Q is present and the data item Q is initially read by transaction Ti. Then in other schedule, which is termed as S prime, in that schedule S prime also the data item Q must be initially read by Ti also. That means in both the schedule S and S prime, the data item Q should be initially read by Ti. If in any schedule S, if the data item Q is read by transaction Ti initially, then schedule S prime also transaction should initially read the data item Q. So this is the initial read queue operation. Next, I will discuss the concept three, then I will come over to. So this is the first concept. It is known as the initial read. Next, final write. The third property is termed as sometimes final write. What it says, for each data item Q, the transaction that performs the final write queue operation in schedule S must perform the final write queue operation in schedule S prime. What does it mean? Suppose if a transaction Ti performs the final write queue operations, that means Ti is the last transaction which performs the write operation on the data item Q in schedule S. Then in schedule S prime, transaction Ti must be the last transaction which must write the data item Q. So this is same as the initial read queue operation. So initial read queue, if transaction Ti reads the value of Q in schedule S, then in schedule S prime, Ti must be the first transaction which should read the value of q. Same is applicable for write q also. If a transaction ti is the last transaction which performs the write queue operation in schedule S, then in the schedule S prime, transaction Ti in same transaction must perform the final write queue operation. Next, the condition 2, for each data item Q, if transaction Ti executes read queue in schedule S and that value is produced by transaction Tj, then transaction Ti must in schedule S prime also read the value of Q that was produced by transaction Tj. So what does it means? And this property also known as the intermediate read operation. So what does it mean? Suppose in schedule S, suppose transaction Ti read a data item Q and that data item Q was previously written by transaction Tj. So this happens in schedule S. So if that happens in schedule S, then schedule in S prime, Ti must be the schedule which is reading the value of Q that should be the produced by transaction Tj also. So all these three conditions actually will be get more clear if we explain it with an example. Let's discuss it with an example. So two schedules are given. This is the schedule 1 and this is the schedule 2. So schedule 1 and schedule 2 both have two transactions T1 and T2 respectively. Both have same schedule T1 and T2. Now the question is whether schedule 1 and schedule 2 are view equivalent or not. Now we can say that schedule 1 is view equivalent to schedule 2 if the three conditions are met or three conditions are satisfied that I have discussed in previous slide. So let's check whether three conditions are satisfied or not. So what was the first condition for initial? The first condition states that the transaction which reads the initial value of Q in schedule S, then in schedule S prime the same transaction should read the initial value of Q. Let's check whether this is true or not for these two schedules. Suppose consider, let me mark with that. Suppose consider first consider the data item A. So in that schedule data item A, which transaction among T1 and T2, which transaction reads the initial value of A? Clearly visible, T1 is the transaction which reads the initial value of A. So we have to check whether in schedule 2 whether the initial value of A is read by T1 or not. Let's check. Here we can see that the initial value of A is read by transaction T2. Once T2 reads the initial value of A, then only the value of A is read by T1. So initially the T2 reads the initial value of A, but here the initial value of A is read by T1, but here the initial value of A is read by T2. So the first condition itself is not satisfied. So no need to check for other two conditions. So straight away we can say that schedule 1 and schedule 2 are not view equivalent. Now consider another example. Schedule 1 and schedule 3, two schedules are given, schedule 1 and schedule 3, and both have same set of transaction T1 and T2. Now question is whether schedule 1 and schedule 3 are view equivalent or not. So again the same thing we have to check. Three conditions we need to check whether they are satisfied or not. So what was the first condition? So the first condition that we have to check is in schedule S the transaction which reads the initial value of A, in schedule S prime also the same schedule should read the initial value of A also. That means is known as initial read operation. So let's check whether this is satisfied or not. So if you consider the first data item A, so here in schedule 1 the data item A initially read by transaction T1, and here in schedule 3 also the data item A is initially read by transaction T1. That means the first condition is, we can say that partially true. We have checked it with only data item A. Now apart from A, we have another data item B also is there, so we have to check for data item B also. Data item B is initially read by transaction T1. Now if you check it here, data item B, where it is data item B, here the data item B is initially read by transaction T1 also in schedule 3. So that means the data item A and B, both the data item are initially read by transaction T1 in schedule 1, and schedule 3 both the value A and B both are also initially read by transaction T1 in schedule 3 also. That means the first condition is totally satisfied. Next, if you want remember the condition 3, we have to check that what was the condition 3, just opposite of condition 1. Condition 1 is initial read, the opposite of initial read is initial write operation. So condition 3 states that if in schedule S the transaction which finally performs the write queue operation, the same transaction should perform the write queue operation in the schedule S prime also. So let's check whether the condition 3 is satisfied or not. So first consider the data item A. So which one is performing the final write operation on data item A? So here write operation on A is performed by T1, but here this is the final write operation on data item A, and the ultimate write operation on the data item A is performed by T2. Let's check whether this is also happening in 3 or not. This is the write A operation, then final write A operation is done by T2. So A is finally written by T2, here also A is finally written by T2 in both the schedule. Next we have to check for data item B also. Now for data item B, data item B is written by T1 here, and finally data item B is written by transaction T2 in schedule 1. Now we have to check the schedule 3. Now write B operation, here is the write B operation, this is performed by T1, and another write B operation is here, and that write B operation is final write B operation which is executed by transaction T2. So in both schedule 1 and 3, data item B is finally written by transaction T2. So condition 3 are also satisfied. Next we have to check whether condition 2 is satisfied or not. If you remember what was the condition 2, condition 2 states that if in schedule S, if a transaction Ti reads a data item Q which is previously, if a transaction Ti reads a data item Q which was previously written by transaction Tj in schedule S, then in schedule S prime also the transaction Ti should read a data item Q which was previously written by transaction Tj. Let's check whether the condition is satisfied or not. So check with the schedule 1 first. So first consider the data item A. We have to check for both the data item. First we have to consider the data item A. So this is the data item A, suppose. So now transaction T2 reads a data item A which was previously written by transaction T1. That means here transaction T2 reads the data item A which was previously written by transaction T1. So same sequence should appear in schedule 3 also. Let's check. This is the read A operation. So T2 reads the data item A which was previously written by T1. So that means this is true. Next check, we have to check for data item B. So data item B is read by transaction T2, and that data item was previously written by transaction T1. Next let's check whether this is true or not for schedule 3. Now what is the data item B? Read B. So this is the read B operation. So data item B is read by transaction T2, which was previously written by transaction T1. So that means in both the schedule 1 as well as 3, the data item A is read by T2, which was previously written by T1. Similarly, for both the schedule, the data item B is read by transaction T2, which was previously written by transaction T1. So second condition is satisfied. So that means for schedule 1 and 3, all the three conditions are satisfied. That is why we can say that schedule 1 and 3 both are view equivalent. Now next, discuss about the concept of view serializability. Now when we can say that a schedule is view serializable? Now a schedule S is view serializable if it is view equivalent to a serial schedule. Means if a schedule is equivalent to a, if a schedule S is view equivalent to a serial schedule, then that schedule is termed as view serializable. Let's take an example. Schedule 3 are given, schedule 1 and given, schedule 3 and 1 both have same set of transaction T1 and T2. Let's check whether schedule 3 are or is view serializable or not. So again we have to check the same concept, means we have to check for view equivalent or not. Schedule 3 and schedule 1 are view equivalent or not, we have to check that. So same three condition we have to check for schedule 1 and schedule 3 also. So start with schedule 3. The first condition was the initial read, means initial read, again I am repeating, initial read means the transaction which reads the initial value of Q in schedule S. In schedule S prime, the same transaction should read the initial value of Q. So if you consider the value of A in schedule 3, the initial value of A is read by T1. In schedule 1 also initial value of A is read by T1. Now consider read B for the data item B. Here also the initial value of B is read by T1. Here also initial read B is performed by T1 also. The first condition is satisfied. Now condition number 3, then I will discuss the condition 2. So the condition 3 is the just opposite of condition 1 and it is termed as the final write operation. What it says, the in schedule S, the transaction which performs the final write Q operation, then in schedule S prime also the same transaction should perform the final write Q operation. So let's check. So write A operation, which one performing the final write A operation? This one. Transaction T2 performs the final write A operation. Here is the write A, but final write operation is performed by transaction T2. So in both the cases T2 performs final write A operation. Now we have to check for B. So which one perform the final write B operation? This is the write B, but not the final one. This is the final write B operation performed by T2. So we have to check it here. This is the write B operation by T1, but not the final write operation. Ultimately, finally, the transaction T2 perform the write operation on the B. So in both the cases, both the schedule, the data item B was finally written by transaction T2. So condition 3 is also satisfied. Now we have to check for condition 2, means intermediate read operation. So start with schedule 3. First consider the data item A. So transaction T2 reads a data item A which was previously written by transaction T1. So that means T2 reads a data item A which was previously written by T1. Same is happening or not? Let's say here this is the read A. So data item A is read by transaction T2 which was previously written by T1. So this is true. Next we have to check for data item B, read B. So this is the read B. So data item B is read by transaction T2 which was previously written by transaction T1. Here also the read B operation is performed by transaction T2, which was previously written by transaction T1. So that means the intermediate read operation, that property is also satisfied for schedule 3 and schedule 1 also. So that means all the three conditions are satisfied. So what we can say that schedule 3 is view equivalent to a schedule 1. Now come to the point, if a schedule is view equivalent to a serial schedule, then the schedule S is known as view serial S. Now here schedule 3 is view equivalent to a schedule 1, and schedule 1 is a serial schedule. If you look at here, all the instruction of a particular transaction are appeared together. All the instruction of a transaction T1 appeared together. All the instruction belongs to transaction to appear together. That means it's a serial schedule. That means schedule 3 is view equivalent to a schedule 1, which is a serial schedule. That means we can say that schedule 3 is a view serializable. First of all, schedule 3 and schedule 1 as view equivalent, because both have satisfied the three properties. And as schedule 3 is view equivalent to a schedule 1, and schedule 1 is a serial schedule, that is why we termed schedule 3 as a view serializable schedule. Another important point, very notable point, every conflict serializable schedule is also a view serializable. Means if a schedule is conflict serializable, then we can say that the schedule is also view serializable. But there are view serializable schedule are there, those are not conflict serializable. Means if a schedule is view serializable, we cannot straight away tell that that schedule is also conflict serializable. This is not the case. The next topic is recoverable schedule. Now before discussing what is recoverable schedule, just let's recap something. Suppose a transaction is executing in a system. Now already I have discussed that not every transaction is supposed to complete successfully. Some transactions are there, those are failed to complete that execution successfully. But the question is, what happens if a transaction fails at intermediate point of time? The thing is that to ensure the atomicity property, what we have to do, we have to do the undo. Undo means we have to undo the effect of whatever the changes it has made to the database. We have to restore the database to the previous state, which was before transaction executes. Means again I'm repeating, if transaction fails at any intermediate point of time, means transaction is not able to complete its execution successfully, then what happen? To ensure the atomicity property, we have to roll back. We have to roll back the transaction. Now rollback means when the transaction has failed to execute, then we have to undo the all the effect that it has made on the database. Now undo the effect means we have to restore the database to the previous state which was is in before the transaction start executing. So this is the simple case. If system execute only one transaction, just we have to roll back. So for single transaction, if it is executing a system, to ensure the atomicity, just we have to roll back the transaction. But the problem is, if more than one transaction are executing in a system concurrently, then we have to address the effect of transaction failure. So this is the problem. Now let's take an example first, then I will discuss the recoverable schedule. Consider the transaction which is shown here. Let me mark it. So this is the transaction. Two transactions are there running concurrently, T8 and T9. Now here point, very important point, notable point, just concentrate on here, is that the T9 and T8 are executing parallelly, and transaction T9 is dependent on transaction T8. Again concentrate here, I'm repeating, transaction T9 and T8 are executing parallelly, and T9 is dependent on transaction T8. Why we termed it dependent? Because if you look at the statement over here, the transaction T9 reads a data item A which was previously written by transaction T8. That means whatever the data item is updated, whatever the thing is updated on the data item A by the transaction T8, same thing is going to be read by transaction T9. That means T9 will read the value of A which was previously written by T8. So that means T9 will read the value of A whatever it has been written by T8. That is why T9 is dependent on T8. And if that kind of dependency is there between the concurrent schedule, then we have to concentrate on how to handle the transaction failure. Now suppose consider the transaction T9 has a single transaction. Suppose T9 has a single transaction, only read A. Once TA is completed, read A is completed, transaction T9 commits. Commits means I have already discussed in the previous lecture. Commit means if transaction performs the commit operation, then all the changes that it has made on a particular database are saved permanently. Then you cannot alter. So after read A operation, this is the single statement T9 performs the commit. Now suppose at that point of time, suppose T8 fails. That means failure has occurred for transaction T8. So rest of the instruction of T8 is not able to execute. So T8 ultimately fails. So what we have to do to make the consistency, to make the atomicity property, we have to roll back. We have to roll back the transaction T8. To roll back the transaction T8 means we have to restore the database to the previous state before transaction executes. So we have to restore the database A. So if we roll back, if we restore the database A, that means the data item read by T9 is wrong one, because whatever the updation it has made by T8 is again restored to the previous state. So T9 should not read the updated value. So that means we have to roll back the T8. As T8 is rolled back and T9 is dependent on T8, so T9 also needs to be rolled back. Why? T9 is dependent on T8. As T8 is rolled back, so T9 should also be rolled back. But T9 has already been committed. So if a transaction has already been committed, you cannot roll back. Why? Because commit means all the data item it has saved in the database in a permanent fashion. You cannot alter. So you cannot roll back transaction T9. That means that kind of schedule is known as non-recoverable schedule. Is non-recoverable schedule. Non-recoverable schedule. And that kind of schedule is not desirable. So non-recoverable schedule is not at all desirable in a system. So what we have to do, we have to design a schedule which is recoverable schedule. As again, let explain the example with an daily life example. Suppose in a class, suppose I have given two tasks to a student. Suppose student X is there. Just concentrate on that. Suppose two students are there. One student is X, the other student is Y. I have given a task to both the student. And what the task is, suppose I have given a task X and I instructed X to complete a particular job, complete a particular job, and whatever the result you are getting, give it to y, give it to y, and what y will do, that result will be published by y. Suppose this is the calculation of average marks of student. Whatever the average marks is calculated by student, that marks is given to y, and y just what he have to do, he have to just publish it into the notice board. Okay, and after that, again I instructed the student x to perform another job which is related with, say, on the previous job. So again I am repeating, I have given a job to x. Now in the job, suppose the job is calculating the average marks of student, and after completion of that job I instructed student x to submit it to student y. Student y is going to publish the average marks to the notice board, and in the meantime the x again do is another job. So this is the another job, will continue to do that. And what happen is that y is assigned to only one job. Whatever the result he will get from x, will publish the result, and once it is published, suppose y go back to his or her hostel or home, because the job is done for y, and y is go back to the home. Now what happened at that point of time, when x perform the another job, it may appear that x able to identify that whatever he has done in the previous job is totally wrong. Means while doing that job, x discovered that whatever he has done previously while calculating the average marks, all the calculation he has made are wrong. So what happened, that means it will consider as x has failure his job. So what happened, x again have to go back to the previous job, then reload all the initial value, means reload all the initial marks of student, and again calculate the average marks from scratch, means from at the very beginning you have to recalculate all the marks. But what happened, y already has been posted the result and go back to the home. So x, though the x is able to recalculate all the average marks from beginning, but as y has gone back to his home or hostel, so the new result cannot be given to y no more. So whatever the result is published in the notice board by y is wrong. So this is the case is happening with that schedule, and that kind of scenario is known as non-recoverable schedule. So we have to ensure that schedule should be recoverable. Now a recoverable schedule, what is recoverable schedule? A recoverable schedule is one where two transactions are executing concurrently, Ti and Tj, and if a transaction Tj reads a data item which was previously written by transaction Ti, then commit operation of Ti appears before the commit operation of Tj. So this is the non-recoverable. Now how to make it recoverable? Now if you look at, say this is Tj, say this is Tj, let me mark it again. So this is Tj, and say this is Ti. Now Tj reads the data item A which was previously written by Ti, then commit operation of Ti should appear before the commit operation of Tj. That means what happened, though the transaction T9 performs the final statement, but still you cannot commit here, you cannot commit to make it recoverable. Means why? Because T9 reads a data item A which was previously written by transaction T8, then commit operation of T8 should appear before the commit operation of T9. That means first commit should be done by T8. Once commit has been done for T8, then only here commit can be done by T9. So the dependent transaction here, the T9 is the dependent transaction, so the dependent transaction should commit last. So Ti T8 should first commit, then T9 should commit. Then that schedule will become recoverable schedule. So this is the concept of recoverable and non-recoverable schedule. Next topic is cascadeless schedule. So again, take an example. Suppose consider the schedule. Again here, if you look at transaction T11 performs a read operation on A which was previously written by T10. That means T11 is dependent on T10. And if you look at T12 reads a data item A which was previously written by T11. So T12 is dependent on T11. So three transactions are running concurrently and these three transactions are dependent. T12 is dependent on T11, T11 is dependent on T10. Now what happens? Suppose commit operation of T10 is here. Let me mark it. Suppose this is the commit operation of T10. Next, this is the commit operation of T11. Next, the commit operation of T12 to make it recoverable. Recoverable means T11 as dependent on T10. So T10 commit last. First T10 should commit, then T11. As T12 is dependent on T11, so T12 commit last. So this is the commit operation. Now what happened? It may happen that at that point of time, before committing T10, what happened? Transaction, suppose T10 fails. Before committing T10, transaction T10 fails. So what happened? We have to roll back. Suppose this sign of rollback. So we have to roll back T10. As T10 is rolled back and T11 is dependent on T10, so we have to roll back T11 also. Now as T12 is dependent on T11, so we have to roll back T12 also. Again I am repeating, suppose before committing here T10 failed to execute. So what happened? We have to roll back T10. Now as T11 is dependent on T10, so we have to roll back T11 also. As T12 is dependent on T11, so we have also need to roll back T12 also. So that means a single transaction failure leads to a series of transaction rollback. Here only transaction T10 failed to execute. That is why we need to roll back series of transaction rollback. So a single transaction failure leads to a series of transaction rollback, and that kind of schedule is known as cascade schedule. Now we have to make sure that, so this is known as cascading rollback also. So in a schedule, cascading rollback should not occur. This is not desirable at all. Cascading rollback should not occur. And if a schedule has no cascading rollback, that schedule is known as cascadeless schedule. Again I am repeating, if in a schedule there is no cascading rollback are there, then the schedule is cascadeless schedule. And when the cascadeless schedule will happen? For each pair of transactions Ti and Tj, such that Tj reads the data item which is previously written by Ti, then the commit operation of Ti appear before the read operation of Tj. So if you remember the recoverable schedule, then what was there? The commit operation of Ti appear before the commit operation of Tj. But here the modification what has been done in cascadeless schedule is that the commit operation of Ti appears before read operation of Tj. So here is the modification. In the recoverable schedule, it was the commit operation of Ti appears before the commit operation of Tj. But here in cascadeless schedule, to make a schedule is cascadeless, modification what has been done? The commit operation of Ta appears before the read operation of Tj. So that means before the read operation on the data item A by T11, commit should be happen for T10. Similarly, before the read A operation of T12, commit operation of T11 should happen here. Before read A starts by T2, T11 should commit. Similarly, before T11 reads the data item A, T10 should commit. And from here we can say that every cascade delay schedule is also recoverable. But if a schedule is recoverable, that does not ensure that it is also a cascadeless. But if a schedule is cascadeless schedule, then it also is recoverable schedule. And it is very much desirable to restrict the schedule to those that are cascadeless. The next concept is testing for serializability. Means we can check whether a schedule is serializable or not. We can check it with the help of either conflict serializability or with the help of view serializability. With the help of this conflict serializability or view serializability, we can check whether a schedule is serializable or not. Now, apart from this, we can have another easy technique so that we can check whether a schedule is serializable or not. For that, we need a graph. We need a directed graph called precedence graph. Consider a schedule which consists of set of transaction T1, T2, T3 tn. Now with the help of this set of transaction, we are going to make a precedence graph. Now as the graph which consists of is represented by G is equal to V and E. So this is the general way to represent any graph. Now precedence graph is also represented in that form, where V is set of vertices and E is set of edges. Now here vertices V correspond to transaction. So vertices, here transaction are represented as a vertices, and edges, this is the edges. Now how to draw edge? So you can how to draw an edges? We can draw the edge between the two transactions if these three conditions, if any one of these three conditions are satisfied. We can draw an edge from Ti to Tj if either Ti execute write queue before Tj executes read queue, or Ti executes read queue before Tj executes write queue, or we can also add an edge from Ti to Tj if Ti executes write queue before Tj executes write queue. So again I'm repeating, first we have to represent the schedule with the help of precedence graph, and here precedence graph is directed graph represented G is equal to V comma E, where V is a set of vertices. Transactions are represented as a set of vertices. If you look at the example, these are the vertices and two vertices are there, means two transactions are there, T1 and T2, and these are the edges, represented by E. Now we can draw an edge from T1 to T2 if T1 executes write queue before T2 executes read queue, or if T1 execute read queue before T2 execute write queue, or T1 execute write queue before T2 execute write queue. So let's take an example. Suppose schedule 1 is given. Now we have to check with the help of precedence graph whether schedule 1 is serializable or not. But before that, we have to first make a precedence graph first. How to make a precedence graph from schedule 1? So how many transactions are there in schedule 1? 2. So we have to represent it with the help of vertices. So this is for T1 vertices and this vertices is correspond to T2. Now we have to draw an edge. So edge, the direction of edge, either it is from T1 or T2 or T2 to T1. We have to make that decision based on previous lecture what I have already discussed based on three conditions. Now here if you look at read A operation is performed by T1 before the write A operation. If you go back to the previous slide, Ti execute write queue before Tj execute read queue, or Ti execute read queue before Tj execute write queue, or Ti execute write queue before Tj executes write queue. If any one of these three conditions are satisfied, then we can draw a line from Ti to Tj. So go to the example. If you consider data item A, so read A is performed by T1, and then write A is performed by T2. So that means H should be from T1 to T2. Also, in other way, simpler way, you can check that as all the instruction of T1 appears before transaction T2, so that means T1 execute first, then T2 execute. So that means T2 is dependent on T1, so that is why the age should be on directed on T2. Or other way, as per the three condition that I have discussed, the read A operation is done by T1, then the write A operation is done by T2. So A should be on direction into T2 direction. Well, let me explain it. Suppose the write A operation. You can check for other also. Write A operation. If you look at here, you can check for any data item or any operation. If you consider write A operation, now T1 performs the write A operation before T2 execute the write A operation. That is also the condition 3. So you can draw an edge from T1 to T2. So next, move to the next example. So this is another example. Schedule 4 is given. Two transactions are there. So T1 and T2. That means in a precedence graph, we should have two vertices. This vertices is for T1, this vertices is for T2. Next we have to decide the edges. Now here if you look at, we can draw an edge from T1. So T1 and this is T2. We can draw an edge from T1 and T2 if any one of the three conditions are satisfied, which I have already explained. So let's check. The read operation, read A is performed by T1 before write A by T2. So TA perform the read operation before T2 performs the write A operation. So that means we can draw an edge from T1 and T2. So this is the edge from T1 and T2. Now let's check whether can we draw an edge from T2 to T1. Let's check. Suppose consider read B. So T2 performs the read B operation before T1 performs the write B operation. So yes, we can add an edge from T2 to T1. So in the previous example, the graph was linear, no cycle was there, but here the precedence graph has cycle. And if a precedence graph contains cycle, then the schedule is not a serializable schedule. And if a graph or precedence graph does not contain any cycle, then the schedule is serial schedule. Means the schedule is serializable. So what I have already discussed, a schedule is conflict serializable if and only if its precedence graph is acyclic. Means if a graph is acyclic, means if the precedence graph has no cycle involved in it, then we can say the schedule is conflict serializable. But if a precedence graph has cycle in it, then it is not a conflict serializable. And there is a cycle detection algorithms are there, which takes complexities order of n square, where is the number of vertices, and is the research level thing. We can devise our algorithm, cycle detection algorithm, which takes which complexity is lower than order of n square. This is our out of scope in our syllabus. And if the precedence graph is acyclic, then serializability order can be obtained by topological sorting of the graph. And this is a linear order consistent, definitely no cycle is there, so it's a linear order consistent with the partial order of the graph. For example, a serializability order of a schedule A, it may be A or B, whatever it be, would be first T5, then T1, then T3, then T2, then T4. Means first T5 will execute, then only T1 execute, then only T3 execute, like that. And that's it for today, and these are the references you may go through for more details.